Chapter 2.8, quick review, problems 1 through 10, and section 2.8 in our book has to do with solving polynomial inequalities. And so these are exercises leading up to that. In exercise 1 through 4, use limits to state the end behavior of the function. So in the end behavior, we're not interested in what happens all in the middle. We're interested in what happens at the very end and very beginning of the function. And to do that, we look at something called the leading term. Okay, the leading term is the highest powered of the polynomial terms in a function. So this is what's called the leading term. And when it comes to end behavior, it's like all this other stuff doesn't matter. So it's 3x squared minus 2x plus 1. That doesn't matter, at least when it comes to end behavior. Doesn't matter with end behavior. So basically, if we look at the parent function of a leading coefficient, and the parent function is f of x equals x cubed. And if we just conceptually, if we have the right drawing conception of what this x cubed function does, then we have an understanding of what our end behavior is going to be. So the x cubed function, if you graph the function, depending on your scale, will look something like this. And we'll start low and end high. And so when it comes to end behavior, which you write as limit as x approaches infinity of f of x, as we go more positive with the x's, what happens to the y's? Well, they go more positive, so we have infinity. And the other end behavior is we go limit as x approaches negative infinity of f of x is equal to, I'll make a more legible infinity symbol down here, I hope. Yeah, it's a little better. All right, as we go toward the left, toward x equals negative infinity, we're going down, or coming from the bottom. So we have negative infinity. So this would be our end behavior right here boxed in. Next, odd number problem 3. Okay, in this case we have a fractional representation. We have to look at the leading coefficients. Well, we have a complication because while in the numerator we have this leading term, x cubed, we have in our denominator a x to the first power. So in determining effectively what our leading coefficient is, we need to take our leading coefficient of the numerator, which is x cubed, divide that by the leading coefficient, leading term of the denominator, leading term of the numerator over leading term of the denominator, we're going to x cubed. And in spite of the fact, okay, we are going to have a discontinuity at x equals 2, because if x is 2, we're dividing by 0. And I don't think this function up above, x cubed minus 2x squared plus 1, I don't think that's factorable. So I think we have a vertical asymptote somewhere at x equals 2. So basically, we're looking at the behavior. If we understand the behavior of x squared, the parent function, f of x equals x squared, we can find our end behavior. And the x squared function is simply the quadratic parent function, right? Y, or f of x, equals x squared. And our end behavior should be pretty easy to ascertain. We have limit as x approaches infinity of g of x, it gave us a g instead of an f here, equals, as we go toward the right, toward positive infinity, x, y goes toward, or f of x goes towards positive infinity. And the limit, as x approaches negative infinity of g of x, is also, as we go toward the left, we also go up, or we come from on high. So this is an example of an even positive function. So this would represent our end behavior. And what I want to do is just kind of show you a graph before making this video on a calculator. And here's our function graphed. And we see, as we predicted, right, we have a vertical asymptote at x equals 2, but our end behavior, right, it's just a quadratic function. It just looks almost like a parent quadratic function, kind of, except for this vertical asymptote, infinite discontinuity, right in the middle. It's a non-removable discontinuity, by the way, because if we factor out what's on top, which I don't think we can do, we're not going to be able to remove algebraically what's on the bottom there. So therefore, our vertical asymptote. Okay, problems, exercise 5 through 8. Combine the fractions and reduce your answer to lowest terms. So what you're looking for in these situations, you are looking for a least common denominator. Okay, I think that's a correct spelling, denominator. And we have a denominator of x in this second term, 5 over x, but we don't have that same denominator here. So what we do is our common denominator is going to be x. So if we take our first term in this expression, which is x squared, to get our common denominator, we can multiply this expression by x over x. And then we just add the 5 over x. And x squared times x is x cubed. So you have x cubed over x plus 5 over x. And since we have our common denominator of x now, we can just write this as a single fraction. But we have x cubed plus 5 over x. So that's going to be our reduced fraction to lowest terms. Next odd number problem, which is 7, we have x over 2x plus 1 minus 2 over x minus 3. So our least common denominator is going to be multiplying these two separate denominators together. So we have 2x plus 1 times quantity x minus 3. When I say the word quantity, I mean that what I'm going to say next after quantity you have to put in parentheses. So when I say quantity, I mean open parentheses, write those two things, something plus something, something minus something, close the parentheses. And so to rewrite this first fraction here, we have x over 2x plus 1, and to get our common denominator of 2x plus 1 times quantity 2x minus 3, we multiply the numerator and the denominator by quantity x minus 3. So here we have x minus 3 in the numerator and the denominator, which doesn't change the basic nature of this fraction, right? That's going to be the same. Then we have minus 2 over quantity x minus 3. And what do we need to do to get our common denominator? Well, we just need to multiply our denominator by quantity 2x plus 1 And then since we multiply the denominator by 2x plus 1, we got to multiply the numerator by 0.2x plus 1. And one way of looking at this, it's kind of like if you look at the original fraction, it's kind of like almost like cross-multiplying this x minus 3 with this x over here to the left term and this 2x plus 1 to this by 2 over here. So that's one way of kind of a shortcut. But anyway, we can now distribute x times x times negative 3. So we have x squared, x times x squared, minus 3x. And we still have this thing here, quantity 2x plus 1. Quantity 2x plus 1 times quantity x minus 3. And then we're going to subtract out minus, we have 2 times 2x and then 2 times 1, so we have minus 4x, 2 times 2x is 4x, and 2 times 1 is 2, so say plus 2. Over the same thing here, quantity x minus 3 times quantity 2x plus 1. So now we're able to rewrite this thing as a single fraction in lowest terms, and to do that, we're going to combine like terms. Okay, now we're going to have one common denominator, which is going to be quantity 2x plus 1 times quantity x minus 3. And here we have x between everything here. On the left term, we have x squared. And we're going to have negative 3x, and that's going to be minus 4x. So we're going to have minus 7x. And then we just have this plus 2, which is actually going to be minus 2 because this minus distributes to that plus here. So we have minus 2. So this is going to be our single fraction reduced to our lowest terms. Oops, I forgot that. Close the parentheses in the denominator. There we go. Okay. We have problem 9. Exercise 910. List all the possible rational zeros of the polynomial and factor the polynomial completely. So for this, we use something that you might remember called the rational, we call it rational roots theorem or rational zeros theorem. And that is, the rational roots or rational zeros theorem has to do with using the leading coefficient of the highest powered term, or the leading term, which is 2, and the leading coefficient of the last term, in this case, which is the constant term 3. So what we're going to get is our possible rational zeros. Okay, they're going to be, what you do is you take plus or minus, and you take the last term, all the factors of the last term. So we have 3, 1 and 3. So 1 times 3 are the possible factors of 3. And in the denominator, we take the leading term of the leading coefficient of the leading term, which is going to be 2, which has the factors 1 times 2. And so what we have is, this leads to, we're going to have 1 we're going to have, these are all plus or minus. We have plus or minus 1, right, because 1 over 1, and then 1 over 2. So we say plus, everything's plus or minus. So plus or minus 1/2. And then we have, now the 3, we have 3 over 1 plus or minus 3, or 3 over 1. And finally, we have plus or minus 3 over 2. So we have 8 possibilities of zeros here, and we have a cubic polynomial expression here. And so what that means is we're only going to be able to use 3 of these 8 possible zeros. What I like to do is take the easiest numbers algebraically to work with, which in this case would be 1. So if I go ahead and take 1, and also that makes synthetic division easy. So I just draw a synthetic division bracket, and we're going to test out the factor of x minus 1. And for x minus 1 as factor, okay, I'm going to write that down more concretely. I'll say test to see if x minus 1 is a factor. Because in factoring, well, we're in part B. Okay, this is part A up here. We've already answered part A. These are the possible rational zeros right here, 8 of them. Okay, so for this one here, you're going to have x equals 1 is your 0. We said x minus 1 equals 0. Our 0 is going to be 1. So we're testing this plus 1 effectively. So we put 1 on the outside of the bracket here, and then the coefficients of the polynomial expression, 2x cubed plus 1x squared minus 4x and minus 3, which is our constant. And so if we go ahead and bring down the 2, we have 2x squared. 1 times 2 is 2. 2 plus 1 is 3. 1 times 3 is 3. Negative 4 plus 3 is negative 1. 1 times negative 1 is negative 1. If we add these together, we get negative 4. So we have a remainder. That is our remainder of negative 4. What does that tell us? Well, since that remainder is not 0, we know that 1 is not a 0, therefore x minus 1 is not a factor. Okay, so that's what we have there. Next, we're going to test if to see if x plus 1 is a factor. Okay? And to do that, we're going to have our 0 is going to be x equals negative 1. Well, to do that, to test that, I'm going to make a bracket over here on the left in red. Okay, here it is. I'm going to put negative 1 out here, and I'm going to put the same coefficients here, 2, 1, negative 4, and negative 3. We bring down this 2, so we're going to have 2x squared. Negative 1 times 2 is going to be negative 1. 1 plus negative 2 is negative 1. Negative 1 times negative 1 is positive 1. Negative 4 plus 1 is negative 3. And negative 1 times negative 3 is 3. And as a remainder, we have 0. So we know, since the remainder is 0, we know that x plus 1 is a factor. And then since x plus 1 is a factor, we still have remaining 2x squared minus 1x minus 3, and we get this from up here, 2x squared minus x minus 3, and we can factor this guy out here probably without having to go through synthetic division or something like that. We're going to have 2x, our factors of 2x squared are 2x and x, and we can kind of experiment around here. Let's see, if we have, we're going to have minus 3, so to have minus 3, we're going to have, let's see, minus, we have to have negative 3 times 1. So let's take negative 3 here times positive 1 here, and we get, that's 2x squared, x times 2x, 2x squared. 1 times 2x is positive 2x. Negative 3x times x is negative 3x. And then 1 times negative 3, that's negative 3. So this checks out. So, factored form. Okay, it's going to be, we found that x plus 1 is a factor. So we have x plus 1. And then our factor of what's remaining here, we had x plus 1 also. And then we had 2x, that's quite 2x minus 3. And as far as what zeros that would give us, this, if we set 2x minus 3 equal to 0, we would get 2x equals 3. So x would equal 3 halves. So what that would do is that tells us that rational roots theorem, our zeros would be here, negative 1 and positive 3 over 2. So that would be our answer to B, part B, which we box in. So good luck on your even number problems, and thank you for viewing.